Hey everyone! Welcome to today's video. In this deep dive, we're exploring one of the most groundbreaking ideas in modern physics, the theory of relativity. Many of you have probably heard of Albert Einstein's famous equation E equals sine mc², or the strange notion that time can run slower for an object moving at extremely high speed. These concepts all trace back to Einstein's revolutionary insights about space, time, and gravity. In this extensive discussion, we'll uncover what the theory of relativity is all about, how it works, why it's so crucial to physics, and indeed to our daily lives, and where it manifests in everyday practical uses. Buckle up for a journey through time and space. The historical context. Why a new theory? In the 19th century, classical physics was dominated by Isaac Newton's laws, under which time and space were deemed absolute, and gravity was treated as a force acting at a distance. Yet by the late 1800s, cracks appeared in this classical worldview. Michelson-Morley experiment, 1887. Researchers tried to detect the so-called luminiferous ether that was believed to carry light waves. Surprisingly, no difference in the speed of light emerged regardless of Earth's motion. This result clashed with the expectation that if light traveled through a stationary medium, we should detect changes in its velocity. Electromagnetic conundrums. Maxwell's equations implied that the speed of light in a vacuum was constant, no matter the observer's movement. Traditional notions of velocity addition clashed with that assumption. Orbital oddities. Newtonian gravity couldn't fully explain the peculiar orbit of Mercury around the Sun, which displayed a slight discrepancy known as the precession of its perihelion. Then along came Albert Einstein, a young clerk at the Swiss Patent Office who in 1905 published the Special Theory of Relativity, STR. This shattered the idea of absolute space and time. 10 years later, in 1915, he introduced the General Theory of Relativity, GTR, which radically revised our concept of gravity. Together with quantum mechanics, Einstein's theories established the bedrock of modern physics and transformed our understanding of the universe. Special relativity, rethinking time and space. Let's begin with the Special Theory of Relativity, STR, from 1905, which rests on two fundamental principles. The principle of relativity. The laws of physics, for instance, those governing electricity and magnetism, take the same form in all inertial reference frames, that is, in frames moving at a constant velocity or standing still relative to one another. Invariance of the speed of light. The speed of light in a vacuum, approximately 300,000 kilometers per s, remains constant for every observer, irrespective of how fast the observer or the source might be traveling. Consequences. Time running at different speeds. Time dilation. An object moving close to the speed of light experiences a slower passage of time compared to a stationary observer. One famous illustration is the twin paradox, where one sibling travels at near light speed on a round trip, only to come back younger than the sibling who stayed on Earth. Length contraction. Distances measured along the direction of motion appear shorter to an outside observer if the object is traveling at very high velocity. Relativity of simultaneity. Events that appear simultaneous in one inertial frame may not be simultaneous in another moving frame. A equals sine mc². Probably the single most famous equation in physics, it posits that mass, m, and energy, E, are interchangeable, linked by the square of the speed of light, c. From nuclear power plants to stellar fusion, this relationship underpins why a small mass can release tremendous energy. Real-world illustrations, particle accelerators. In facilities like the Large Hadron Collider, LHC, protons are propelled to speeds near that of light. Their behavior, for example, their increasing relativistic mass and extended lifetimes of certain particles, must be calculated with relativistic formulas to match experimental results. Atmospheric muons. Created in the upper atmosphere, muons should theoretically decay before reaching the Earth's surface. However, thanks to relativistic time dilation, from our perspective, they live long enough to arrive at ground level. E equals sine mc², a small formula with huge impact among the outcomes of special relativity. E equals sine mc² stands out as an iconic symbol. Why is it so significant? Matter-energy equivalence. Even a tiny loss of mass translates into an enormous release of energy. This principle underlies nuclear fission in reactors, nuclear fusion in the sun, and other energetic processes. Star power. Stars, like our sun, fuse hydrogen into helium, converting a portion of the mass into energy that sustains them for billions of years. Nuclear technology. Our ability to harness nuclear power or nuclear weapons stems from the recognition that matter can convert to energy following E=sign mc². General relativity. Gravity as curved spacetime. While special relativity handled inertial motion at constant speeds, with no gravity, Einstein's general theory of relativity, GTR, from 1915 tackled the gravitational realm. He proposed that gravity is not a conventional force, but rather a manifestation of the curvature of spacetime. Main ideas of general relativity equivalence principle. Being stationary in a gravitational field is locally indistinguishable from accelerating in free space. If you're enclosed in an elevator, you can't tell if the force you feel is due to gravity or to the elevator accelerating upward. Gravity as geometry. Massive objects warp the geometry of spacetime around them. Other bodies, including light itself, simply follow the curves in that geometry, which we interpret as gravitational attraction. Gravitational time dilation. Clocks run slower closer to massive bodies. The stronger the gravitational potential, the slower the ticking compared to someone in a weaker gravitational field. Observational evidence, light bending. In 1919, during a total solar eclipse, Arthur Eddington measured star positions behind the sun and confirmed that the sun's gravity deflected their light by exactly the amount predicted by Einstein. Mercury's orbit. Mercury's perihelion precession had puzzled astronomers for decades. Newton's gravity couldn't fully explain it. General relativity does so perfectly. Gravitational lensing. Massive objects, for example galaxy clusters, act as lenses, bending background light from even more distant galaxies and creating ring-like or multiple images. Gravitational waves. In 2015, the LIGO experiment made the first direct detection of gravitational waves emanating from a collision of two black holes, matching Einstein's predictions. Why it matters. Everyday practical examples, GPS, and satellite navigation, general and special relativity join forces in GPS. Satellites orbit the Earth at high speeds, special relativity effect, while experiencing weaker gravity, general relativity effect. Speed. Because satellites travel quickly, their onboard clocks tick slightly slower from the perspective of an observer on Earth. Gravity. Due to less gravitational pull at altitude, those clocks tick faster relative to Earth-based clocks. Combining both factors shows that overall satellite time runs a bit faster. Ignoring these corrections would mean daily positional errors of many meters, rendering GPS useless. Nuclear energy and stellar fusion. The famous E=sign mc² formula clarifies how the sun and stars shine. Fusing hydrogen into helium releases a fraction of the mass as energy. Likewise, nuclear power plants here on Earth rely on converting mass to energy in fission reactors. Astronomy and cosmology relativity is central to modern cosmology. From black holes to the expanding universe, from cosmic microwave background radiation to gravitational lensing, the equations of general relativity define how we model large-scale structures and interpret astronomical observations. Quantum versus relativity. Unanswered questions. Despite the successes of both special and general relativity, not everything is settled. A major puzzle is the lack of a quantum theory of gravity. Quantum mechanics. Great for describing the microscopic realm of elementary particles. General relativity. Great for describing massive objects and cosmic scales. When they collide, in extreme cases, for example, inside black holes or at the Big Bang, the two theories yield contradictions or infinities. Physicists explore possible unified theories, such as string theory or loop quantum gravity, but so far, no solution has been rigorously confirmed by experiment. That means Einstein's framework, while immensely successful, is still part of a bigger puzzle we're trying to solve. Common misconceptions. People sometimes misinterpret relativity as everything is relative, so nothing's certain. That's an oversimplification. Not everything is arbitrary. Einstein's theory posits absolute laws, for example, the constant speed of light. But it shows that measurements of time and space can differ for observers moving at different velocities or experiencing different gravitational fields. He didn't abolish time. Einstein demonstrated that time is interwoven with space into a single four-dimensional continuum, spacetime, and that time flows differently depending on velocity or gravity. Conclusion: a new way to see space, time, and gravity. To wrap things up, relativity, both special and general, overturned our intuitive notions of absolute space and time. Instead, we learn that space and time together form a dynamic arena in which distances, clocks, and the flow of time depend on relative motion and mass. Gravity emerges, not as a conventional force, but as a result of how mass and energy shape the curvature of space-time itself. In modern physics, these insights have become indispensable. They help us predict everything from GPS satellite behavior to black hole collisions. At the same time, the quest for a deeper unification with quantum mechanics continues. Even so, we can say that Einstein's theories remain among the best tested and most significant conceptual revolutions ever in science. I hope you enjoyed this deep dive into the theory of relativity. If you found it enlightening, please give this video a like, consider subscribing for more fascinating science content, and let me know in the comments which aspect of relativity fascinates you most. Is it the iconic E=sign mc², time dilation, or the fact that GPS literally relies on relativity every single day? Thanks for watching, and I'll see you in the next video.